Okay, so that actually finishes off everything we will talk about bridges for the moment at least. So now we know how to local area networks, how to connect them with bridges, how bridges figure out how to build their forwarding table through backwards learning or adaptive learning. And then the final piece to the puzzle was this spanning tree protocol to make sure that we avoid loops in the topology. I was a little bit fuzzy on why we don't want to have loops, but trust me, they're bad, right? So we want to remove them. The topology we get here is not necessarily the best possible one in the sense that there could be better. I mean, there are many ways to build a tree from a topology, and some trees are better than the others. We did not try to optimize this. It just became what it became out of this algorithm. So there are tweaks one can do in order to get maybe better or better topologies than the one that the protocol makes. And one way is to work on the IDs or the bridges. And I didn't say that also, but I got a question in the break. How do we get a bridge ID? Well, each bridge has a MAC address, so we can use that. But then on top of that, one can add a priority to a bridge to sort of encourage that bridge to take the role as a route. So then that requires a little bit of configuration, of course. And then finally, what should I say? Then for the more advanced routing between local area networks out on the big internet, there are routing protocols which are higher up in the stack in the network layer. But we won't talk about that in this course. Okay, so let's continue then, if there are no questions or comments so far. And then talk a little bit about Wi-Fi and wireless. So why do we want to do wireless? Well, it's quite easy. We would like to move around, and then it's inconvenient to have cables. So in some cases there is no choice. So I mean, we don't want this to have a cable connection to the internet, right? We want that to be wireless. And also sometimes it's just too expensive or too cumbersome to draw to deploy wired networks even if we are not moving around so much. So that's just for cost and convenience. So the problem with wireless, what are the problems? And the problem is that the signal strength varies in time and space. So what do we mean by that? Well, it's that the transmit power of this wireless microphone, there is some transmit power here, and that's spread in all directions, and it's picked up by the receiver over there, but only a fraction of the transmitted power is actually reaching the receiver because a lot of it goes in other directions. Okay. So path loss, the power loss over from the transmitter to the receiver could be quite significant, and of course that increases with distance. And also another problem is what's called multipath propagation. So the signal that goes from this microphone to the receiver takes the direct path between them, but also is bouncing off walls and so forth. So that creates a distortion phenomena called fading, which could be quite severe actually, because at the receiver you receive multiple copies of the transmitted signal. Sometimes these are adding constructively and sometimes destructively. If they add destructively, it means that the received signal strength could be very much weaker than the path loss alone would dictate. So there are many problems with this. Another problem is more like a security point of view, that if you do transmission in wireless, it's easy to pick that up if you're close by. You don't need to break into a building and connect yourself to a cable. You could just put up your antenna and you can listen to what's going on. So security issues are there. Third problem is that the radio spectrum is quite limited and overused. It's heavily used, and therefore it's regulated. So we can't just build a wireless system, a product with a wireless system without first get permission to use a certain frequency band for that system. All right, so to summarize, and all of these things we will talk more about in courses that in the MCOM program, for instance. So mobile access then to the internet, there are two main ways to get to the internet, and one is through cellular, 3G, 4G, and soon 5G, or it's Wi-Fi. Those are the two dominating access technologies. We won't talk much about cellular in this course, not at all, actually. So let's just talk about Wi-Fi, because that fits into the story that we have been talking about so far. So Wi-Fi, it's an IEEE standard, so it's 802.11. So if you remember at the beginning, we had the LLC layer, and then we had the MAC layers, we had Ethernet, we had token ring, and we have Wi-Fi, we have a bunch of others, and then we have physical layers below it. So .11 here is the medium access for wireless. And it was stimulated by that in the mid-80s, there was some frequency band that was left open for use without too much regulation. So it's basically, this was done in the US. They opened up a few bands, and then other parts of the world started to do the same. So the Wi-Fi bands, which is in the beginning was around 2.4 gigahertz. But later on, it's been also up in the higher bands here. And there's been more and more bands added to this, and some of them have disappeared also. So the 802.11 work started by around 1991. It took quite a long time before the first version of the standard was released in 1997. So there is a standard called 802.11 version 1997. Which is the first rudimentary Wi-Fis. And then it has now evolved into a very, very diverse standard with many options, with many Mac versions and physical layers. So if you look in the book, for instance, it's not very updated on Wi-Fi at all, because it's since the book is a bit old here. So the current standard here is some 2,800 pages of text in it. It's actually not so bad to read, but it's quite complex, right? And there are many options, but not all options are used in this standard. So I did this last year. I took a snapshot from my Mac and looked at what can we say about the Wi-Fi it was connected to at the moment, and it was connected to a network called Eduroam. It has some security associated with it, some BSSID, some channels, country code, RSSI, noise, transmit rate, physical mode, and modulation coding system index here. So what does all these things mean? Well, let's see, right? Let's try to dissect this. A few things we can say directly off the bat is that this is the received power. Okay, so the RSSI stands for Received Signal Strength Indicator. So at that moment, the received signal from the access point I was attached to had a received power of -75 dBm. And dBm is dB relative to 1 milliwatt. So this is 10 to the minus 7.5 milliwatts is the received power. Okay, is that a lot or a little power? It's very small power, right? I mean, it's I don't know. It's 10 to the minus what? 3, say 10 to the minus 10 watts, right? Quite low, right? What saves the day is that the noise power is even lower, right? Otherwise, we would be in bad shape. So it's this is the noise power, and then the ratio between the signal and noise gives us the signal to noise ratio. So in here, it's like 75 to 90. What is that? It's 15 dB of signal to noise ratio. And this signal to noise ratio tells us which physical layer would be suitable. So the physical layer transmission rates and so forth is adaptive in Wi-Fi. It's adapted to the current signal-to-noise ratio, among other things. So in this case, this 15 dB of signal-to-noise ratio happens to be enough to support 59 megabits per second, a physical layer that does that. And to be more specific, it has a certain variation of this physical layer. We will see about that later on, so what this actually means. But anyways, the RSSI and the noise determines the data rate. So the closer I am to the access point, in general, the higher the data rate is. The further away I am, the less the data rate is. This has to do with the actual physical channel that we're using. So this is a 2.4 gigahertz, and it uses a 20 megahertz channel. This happens to be the MAC address of the access point which I'm attached to at that point, and this is the security protocol that we used. Okay, so let's dive into a little bit more details on how Wi-Fi works. And the problem with any standard is that there is a terminology that could be overwhelming. So some of these terms we need to learn if we want to understand the standard. And sometimes the names are a little bit different from what the names are in the book. But anyway, so well, these things are the same. These are very specific for Wi-Fi. So we have something called the basic service set, and it's identified by a basic service set ID. So what is a basic service set? Well, it's a group of stations that are coordinating their access. So each Wi-Fi network, each Wi-Fi card in here, which is attached to EduRoam, builds up a basic service set. Okay. And all these nodes are located physically in something called the basic service area. So it's maybe this room or this floor or whatever is a basic service area. So stations which are in the same BSS can communicate with each other. But we also know that in this area, if we open up a Wi-Fi connection here, there's probably 3 or 4 Wi-Fi available here. So we can have several basic service sets in the same area. Okay, several networks that we can connect to. An extended service set is identified by this SSID, so EduRoam, for instance. So EduRoam, there is not a single access point for EduRoam, right? Because it's covering the entire campus, and so we have many access points, and all of them collectively builds. Each access point has a basic service set, and all of these basic service sets are then connected through a backbone to form an extended service set, which is all EduRoam. So if I'm connected to EduRoam here, I'm connected to some access point. If I move over to my office, I'm still connected to EduRoam, but probably through another access point. Okay. Yeah. So a picture of this. Oh, okay. So we are also allowing communication which is outside the without access points, and this is sometimes called ad hoc networks. And there is also something called communication outside the context of the BSS, which is really a true ad hoc network with no access points. And this is the main thing in this 802.11p for traffic safety. Okay, so an ad hoc network, what is that? Well, it's a bunch of Wi-Fi nodes that self-organize into a network without any access point to coordinate everything. So it's a temporary association of a group of stations. For Wi-Fi, there are two variations of this. One which is called an independent BSS or IBSS, sometimes called the ad hoc mode, or this communication outside the context of a BSS or OCB. Okay, so 2 variations on how to self-organize a bunch of nodes to start to communicate. So traffic safety is one example of this. Now for the rest of the lecture, we will not talk about ad hoc at all. We will talk about the more way to access the internet through an access point. And these are known as infrastructure networks. So the components of an infrastructure network is that we have access points, And an access point has a basic service area where there are stations. They attach to the access point and are served by the access point. So here we have a basic service set A for access point 1. Here we have basic service set B, where access point 2. So these nodes are then attached to access point number 2. These access points are connected through a distribution system. So we can think of this as an Ethernet, for instance, but it could also be wireless backbone here. So somehow they have a means, the access points have a means to communicate through this distribution system. Attached to the distribution systems, there are special nodes called portals, and these could be then a gateway to the internet. Okay, so basic service set, access point, distribution system, and together they form an extended service set. So think of this as edu-ROM, for instance, and then BSS-A would be the local access point we have here. If I move over to my office, I get another access point, but I'm still attached to edu-ROM. And edu-ROM somewhere, there is a portal out to the internet, a router somewhere. Okay, questions so far? Okay.
One.
Yes?
Those access points, are those like antennas and base stations? Or
yeah, very similar to this. So they are attached with, they have antennas and radio hardware. And then also a means, typically an Ethernet port or something like that, to connect to a distribution system. Right. Yeah. And so data here can flow then within a BSS, and then it can go to another station attached to another BSS, or it can go to the internet. And all of this is transparent to the node itself. It does not need to know where if the destination is attached to the same BSS or not, or if it's attached to the internet. Okay, so these distribution services, as I said, we can transfer data between access points in the same extended service set, between portals and so forth. We can move data back and forth. So this is not rocket science. However, an ESS, this extended service set, for the LLC layer in the station, it looks like it's the same, it's a BSS. So, right. Infrastructure services. So when powering on, we log on to a network, and this is called association. So a station can select an access point and establish an association with it, and then it probably needs to provide a password to do that. Right? And then it can, once we have associated, then we can start to send and receive frames via the access point, and via the distribution system, we can go elsewhere, you know, to the internet, for instance. There's something called reassociation, and that means that we are associated with one access point, but move into the coverage of another access point. So this is sort of like a handover between access points and access point. And this is called reassociation. A Wi-Fi node is associated with one access point, and then when it moves to another access point, it reassociates with the other one. We can also disassociate, which means that we terminate, we log off the network. There is some authenticity service that is to enable that we can guarantee identity of the stations. And there is a privacy service here. And here, in the book, privacy here means secrecy. So it's encryption. It's not privacy in protecting personal data, as the modern word privacy means. Okay. Even if we go back to the standard, they talk about privacy in the standard, but what is meant is secrecy. So what does that mean? Well, it means that if you listen to a Wi-Fi packet in the air, you cannot decode the payload. You cannot read the payload, right? Because you are not, you don't have the, if you don't have the key to the crypto. So we talk more about security on Monday for this. So this is WPA2 is the one which is recommended to be used now. Right, there are some earlier security protocols of Wi-Fi that turned out to be badly flawed. Right, so one should not use those. Actually, it turned out last year that somebody hacked WPA2 also, so it needed to be updated. Yeah, security is not always secure, I think is the message here. Okay, MAC layer, what does it do? Well, it does what MAC layers does. It's responsible for channel access, it's some addressing, formatting, error checking. Also fragmentations and reassembly is done by the Wi-Fi MAC layer. There is some security here, and we'll talk more about that later on. And then it also has to do with the handovers. It figures out this handover between access points, and also has a little bit of power management. Power management is important for battery-powered devices. So you can allow this one to go down to sleep, for instance, to save power. What services does the MAC provide to the LLC? So remember, if this is the MAC layer, below it is the physical layer, above it, since it's an IEEE standard, there is LLC. Okay. Well, it provides transmission of frames, MAC frames, and it's best effort. Okay, so no guarantees for that the data receives that the data reaches the destination. There are actually two ways that the MAC could be built on. There is something called the distributed coordinating function that we will talk about in detail in a while. And then there is something called the point coordinating function here. This PCF, as far as I know, is not used in practice, so we won't talk about that today. But this one has a little bit of scheduling ideas in it. And remember, scheduling is nice if we want to guarantee some performance, for instance. But this is rarely used, if ever, in practice. So Wi-Fi uses this DCF or variations of DCF. And that's simply best effort. Trying to do its job as best as it can, but it doesn't guarantee anything. So, medium access. What type of medium access are we using here? It uses carrier sense multiple access with collision avoidance. Okay. So we know what CSMA is. We talked about that earlier. It's a listen before talk protocol. So you listen to the medium before you start to transmit your frame. And then we talked about collision detection, but here we have collision avoidance instead. So this is new. So we will talk a little bit what that is. So why do we not using collision detection in Wi-Fi? And the reason for this is that collision detection is very hard to use in wireless, typically. Okay? There is research ongoing to try to enable this, something called full duplex radio, but it's still research. I don't know of any products on this. But so the root of the problem here is that the transmitted signal has much higher power than the received signal. So if this is a Wi-Fi device, it transmits Wi-Fi frames to the access point, and then they receive Wi-Fi frames from the access point. The power of the outgoing transmission could easily be 100 dB higher than the power of the incoming transmission. Okay, easily. It could be more than this also. So power difference 100 dB, what is that? Well, it means that the ratio between the transmit power and the receive power is 10 to the 10. So 10 billion, 10 miljarder times higher transmit power than receive power. So if you want to listen to a weak frame coming in, you tune your hardware to that receive power. If you also want to listen to what you transmit, that's 10 billion times higher power than what you are expected to receive. You easily burn out your receiver, right? So if one would do this, basically the receiver circuit would fry, poof, disappear, right? So it's hard to do. Okay, so so that's one problem. So we want to do something else, and this is called collision avoidance. Also, another problem with wireless is that carrier sensing is not perfect. So when you listen to the medium, if you don't hear activity on the medium, it doesn't necessarily mean that the medium is available because of the path loss. Okay, and we'll see an example of this later on. And this will cause collisions and then lost frames. Okay, so a little bit of details then. DCF, distributed coordinating function. So what is it? Well, it's a way of making these Wi-Fi nodes use the wireless network, wireless channel in a good way, and they need to do that also distributed because there is not a central controller here. So basic access services that we transmit frames with best effort, and all station needs to contend for the medium. So the basic ideas are these, and then there are many small details for this to work. It's typically like this, that if you look at the specific standard, a specific system, there are many details or small changes in it in order for it to work, right? But at the core, we have a very basic idea, a simple idea, this CSMA CA basic idea. Carrier sensing, we know what it is. So what is collision avoidance? Well, basically, here we have a time diagram here. So suppose a node would like to transmit something. So it receives a frame for transmission and now would like to access the medium. So we do carrier sensing. So we sense the medium first, and we sense the medium over a specific time period here, which is actually a fairly long time period, namely for something called a diffs period. And diffs stands for distributed coordinating function into frame space, okay, or diffs. So it's a certain number of microseconds, okay? If the medium is busy, okay, we then need to wait until the current transmission is finished. Okay, so this is what we do in CSMA also, right? But then instead in Ethernet, what we did when the medium got was not busy anymore, then we transmitted immediately. Okay, so it was one persistent CSMA in that case. But here we do a back off. Okay, so it's almost like non-persistent CSMA. So we are a little bit more careful in accessing the medium. Okay, so if busy, we wait and then we back off. Okay, so here, if it's idle, however, we transmit, we wait for an ACK, we wait the diffs and then back off. Okay, so we will see this in more detail in a second, but the gist of it is that we have a frame here ready for transmission. The node senses the medium, and if the medium is idle for a diffs, then it transmits its frame and then waits for an acknowledgement. And after a time, the transmission of the frame and the ACK has finished at this point. Then the transmitting node and all other nodes needs to wait for another diffs of idle, and then all nodes back off until the next frame can be transmitted. Okay. This waiting until the medium, that the exchange of the frame and the acknowledgement and the diffs has expired, this is called when we are in deferred access. So no transmissions can occur here except the one which is ongoing. And then the back off here is randomized between the different nodes, and the one that reaches has the shortest back off time wins access to the channel and then can transmit the next frame. Okay, so details, something like this. So we have a source, we have a destination, and we have all other nodes. Okay. So what's going to happen here now? Well, first of all, we wait the diffs. Okay, we need to do that. So the source here listens to the medium, and the medium is idle over the diffs. So now it can start to transmit. So it transmits its frame. And when it transmits its frame, all other nodes can hear that the frame is ongoing, and they know they need to wait. And actually, they need to wait a time here, which is longer than the frame, because there will be also an acknowledgement and a diffs involved in this. But anyways, at this point in time, all nodes that heard this data frame knows that need to wait. So if there is another node that would like to access the channel here, it has to wait. Okay. What happens then is that the data frame reaches the destination, and let's say that it was decoded correctly and everything panned out, and then it transmits an acknowledgement back. And it transmits an acknowledgement back after a time called the CIFS. So what is a CIFS? Well, we'll see that it's actually a short interframe spacing, right, which is shorter than the diffs. And the reason for having a short spacing here is to give priority to the ACK frame. Okay? Because if a node came in and wanted to transmit at this point, it would see that the channel is idle, but it will not be idle for entire diffs, right? Because the idle period here is only a CIFS long, which is shorter than the diffs. So it would never actually be allowed to transmit. Okay. So, and this ACK frame is then received by the source, and now the transaction is completed, data frame plus acknowledgement at this point in time, and then every node needs to wait for a diffs before anything else can happen. Okay. So what happens after here? Well, suppose the source has more data to transmit. It is not allowed to transmit that immediately here. Okay. So this was only for the first frame, right? The second frame, we need to back off before we transmit that. All other nodes also need to back off here. So there is some back off time here, and this back off is random. So suppose here we got 4 slots to back off, and here we got 6 slots to back off. We start to back off, and back off we will see what that means later on, but essentially if the channel is idled over one of these time slots, we reduce the back off counter until we get 0, and then we can transmit the frame. Okay. So this CIFS here is the short interframe spacing, and its length is less than the diffs, and what the meaning of that, what that causes, the implication of that is that it gives priority to the ACK frame over any other data frames. So for instance, if the blue user here would like to use the channel, it will be blocked because the channel is not idle for an entire diffs. It's only idle for a CIFS. Okay. Clear so far? Yeah. Okay. So there are different CIFS and diffs times. It depends a little bit on the standard, the exact if it's 11A or AZ or whatever it is. And it also depends on the channel bandwidth. But for this one, which is a fairly common way to do things, the slot time here, that is the time slot time, is 9 microseconds. The CIFS, this one, is 16 microseconds. And the diffs is a CIFS plus 2 slot times, which is then 34 microseconds in this. Okay. Just to give you a feeling for the numbers here. The numbers are, of course, not important. I will not ask you what the CIFS is on the exam, right, for this particular one. But if you know it, it's 16. Okay, so back-off procedure. How is this done? Back-off period. Okay, the time we wait. Okay, so the back-off time is an integer random number of idle contention time slots. Okay, so what do we mean by that? So a station which is in back-off, it senses the medium, and then it reduces its back-off counter with 1 every time an idle slot has passed. Okay, so what does that mean? Well, so suppose the back-off counter is 3, then we wait for 1 slot, and if the channel is idle over this slot, it then becomes 2. And then after 1 slot, it becomes 1. And then after 1 slot, it becomes 0. Okay, and the transitions is done here: 3 to 2, 2 to 1, 1 to 0. And oops. Okay. So the back-off stops if the medium becomes busy, and then we resume after a diffs of idle medium. Okay, so we count down as long as the channel is idle, but if the channel becomes busy, then we stop. We freeze the back-off counter. A station transmits when the back-off counter reaches 0. So actually, here when we went from 1 to 0, we can start to transmit the frame. Okay, so 3 to 2, 2 to 1, 1 to 0, transmit frame. Okay. The back-off counter, it's a random number, and it's selected inside a certain interval from 0 to a parameter called CW. CW for contention window or contention window size. Sometimes we call this the contention window, and CW the contention window size. So this contention window size, how do we choose that? Well, we choose that between a minimum number and a maximum number, which is pre-specified in the standard. So for 802.11a with 20 megahertz channel spacing, the minimum CW is 15, and the maximum CW is 1023. Okay, so the size of the contention window is dynamic, so it changes. It changes with the situation. And just as in Ethernet, it changes depending on in how many retransmissions we are doing. Okay, so for each new retransmission, we have to back off, and the CW then for each new retransmission is approximately doubled until we get to the maximum number. So the exact formula is like this. So basically, if we start with 15 for the first contention window, so that's the minimum one. It then, if we do a retransmission, it goes to 31. And for this, if that transmission is unsuccessful and we need to do a transmission again, it becomes 63, and so forth. And it keeps on going to that until it reaches 1023. And for each subsequent retransmission, it remains at 1023. Okay. As soon as we do a successful transmission, then we reset the CW to the minimum one. Okay. So we start by being aggressive, short back-off times. If we fail, we increase the range of back-off times. That is, we typically on the average wait more, and then wait more until we get the frame through. When we get the frame through, we become very optimistic again and back off just short time. Questions? Okay. Let's stop here. So we'll talk about carrier sensing and a few other things on Monday. All right.